Suppose you want to find the cube root of 7, and obviously you can't just use a calculator. Well, I want to introduce to you the Newton Raphson approach of finding roots. It doesn't have to just be of a number, it could be of a function, it could be of anything. And what the Newton Raphson approach is it is a, bear with me here, iterative numerical method. Technically. But between you and me, it's just a trick, okay? I don't even know what that means. It's a trick for finding roots. So another way of looking at our problem is, well, if we're trying to find roots, let's make it into a function. Okay, so let's say our root x is the cube root of 7. Okay, then we could also write this as x cubed is 7, or x cubed minus 7 is 0. And this is sort of by definition what a root is, so we can make this our f of x, or our function. And then, deriving this would be 3x cubed, or squared, and then our minus 7 constant would just be 0, so we're just left with 3 times x squared. And given this formula here, we can input our functions in. So r is what we first guess the root to be, so we have to start somewhere, minus our function, and our derivative. And so to estimate, we have to start somewhere, so we have to guess. So I know that 2 to the 3 is around 8. So let's guess 2 for now and try to refine our answer from there. So instead of our placeholder variable, let's say we guess 2. And so all of the x's here become 2. So it'd be 8 minus 7, 3 times 4, which becomes 1 over 12, or we're busting out the calculator. 2 minus... Sorry, bear with me here. Wow, okay. 1.916-ish. And now, okay, it got a bit smaller, which makes sense because 2 cubed was 8, and that's a little bit over 7, so it's natural that it should go down. And if we re-estimate this now, or let's see if it's more accurate, we get 7.3.0337. That's pretty close to our 7. And the whole use of this Newton-Raphson trick is you can keep repeating this process, although it is a little tedious and manual, but you can keep doing it until you refine your estimation. So just for the sake of it, it's not like we're missing time. Let's put it into the formula again. So we put in our new guess, of 1.916 minus 1.916 cubed minus 7 divided by 3 times that squared, which is 1.916 minus, let's do the denominator first, which is 0.3374 divided by times 3, which is 4.2925-ish. Okay, these are estimates. And just a suggestion is the more you try to refine your process, I'd say the more decimal places you want to put, the more accurate you want to become, right? Putting your first guess in, you're not going to be accurate anyway, so you don't have to use that many decimal places if you want to. That's why I only use like 3 here. And so evaluating this, 4.29125. So we get 1.916 minus 0.00786. And I think you sort of get the point. I'm just showing off how accurate it can become and sort of the use case. So 90814. And if you do that squared, well, that becomes 69475. So you see, at first it went a little bit above, but now it went a little bit below. And so if you keep doing that, it'll sort of balance out and come back in the middle. And the sort of intuition behind this is, here, let's look at the actual formula itself, is that if our guess is a bit over 7, then this becomes really small, but it remains positive. So it removes from our guess and makes it smaller. Just like in our first example here, the cube root is a little over 7, and so refining it again, it removed from our 1.916 to make it smaller, to sort of try to balance it out in the middle, and now it's too small. Now it's just below 7. And so I already know if we were to refine it again with Newton Raphson, that it would add on a little bit, because intuitively, our denominator here would then be negative. So this would become plus, and this would add on to our guess. And you can keep doing this until you find a pretty good root, or a root you're satisfied with, depending on the situation and how many decimals you want. And now, of course, this doesn't have to apply to just cube root of 7. How many uses are there for finding roots in math? A million. Okay, so depending on the question, the word question, the function you construct, whatever, this is a useful tool to estimate cube roots if it's too complex. And geometrically, if you think about it, why this makes sense is, let's try to sort of visualize it with a graph. So as mentioned, when it's slightly above, when our guess is slightly above the root, it subtracts. And when it's slightly below, it adds on. So let's think about some random graph. Let's say this is like close to x squared, whatever. And we have some graph. intuitively, what our guess means is for some, here, let's clean this up. Is for some guess, we're just finding what the tangent line is essentially at that point. And so it's saying like, hey, from your guess, it's a little, actually in this case it's not even, it doesn't even have a root. What a bad example. But let's say it crosses right at 0. And our guess crosses here. Well, it's saying like your slope is a little above, so let's remove it, or let's subtract from it because it's too large. And from our other example, from our last example that we did, when we finally refined it refined it too much, and so it estimated our root was a little below. Right, I think it was like 6.91 something, and this was our 0. Or whatchamacallit. Yeah, it was like 7.1 something. I already forget. Anyway, you sort of see the geometric intuition behind here. We're just estimating the slope using guess and sort of refining it until we come to somewhere in the middle, and that's how we estimate the roots intuitively. I hope this method helps you.